Hi, this is Kumar, and today we're going to talk about designing stable emulsions with physics-based modeling, physics-informed machine learning, and optimization. It's part of a series of videos on going from theory to lab-ready recipes using GenAI, AI, and intelligence in general. All right, let's get started. So the goal today is to figure out, basically create a practical, scientifically grounded framework for designing stable emulsions using a combination of physics-based modeling and Bayesian optimization. This approach blends mechanistic insight with data-driven learning, ideal for modern R&D teams. All right. So why do we want to talk about this, and why do we want to do this? What's the motivation? Now, formulation is part science, part guesswork today, but trial and error is no longer acceptable. We need a system that respects physical limits and helps us guide towards viable formulations. So in the real world, formulators will struggle to hit critical stability targets. It's the droplet size or the creaming rate. Current approaches rely heavily on trial and error, and that obviously leads to wasted time, materials, and you see this in the real world as delayed launches. You see recalls of products that have been found to not work in the real world and so on. And so the problem is that pure machine learning models can often suggest physically impossible combinations, and the way you figure out that is by actual testing. And if you are lucky, you can figure it out, but it takes the extra time and the effort and the money required to determine and to do that testing and figure that out. So what you need is a physics-aware, explainable, optimization-friendly solution. It's a system that guides the formulator to a feasible, stable, and shelf-ready emulsion. And the way you do this is by integrating mechanistic logic from PBM plus machine learning and then optimization. Once you put all of these three things together, you have the most optimized, fastest, least error-prone, least wasteful approach to creating these formulations. So let's first spend a few minutes on what is physics-based modeling. So you want to think about this as the digital twin of the lab. It simulates experiments before wasting time and materials. It's deterministic, it's grounded in science, which makes it extremely trustworthy. It's a scientific compass. It ensures that all predictions are physically valid. We're not just relying on black box models. PBM can anchor us to what's chemically and physically possible. So it uses equations from fluid mechanics, thermodynamics, and colloid science to do things like predicting droplet size based on mixing energy and emulsifier properties, estimating creaming rate using Stokes' law, simulating shelf Arrhenius law. There are a few key equations that are very relevant to this specific problem: droplet size and rate, epsilon, interfacial tension and density, law with droplet diameter and oil-water density difference, and shelf life, Arrhenius, decay of physical stability based on temperature and activation energy. Given an all-type emulsifier, mixer, and the RPM, we can compute the droplet size using fluid mechanics. We then estimate creaming rate using density and viscosity. Shelf life can be simulated using kinetics, and every result is constrained by the physics. So no unscientific guesses here. This ensures that only feasible results are sent to the next step. Before we move on, let's talk about what a Gaussian process is. Now again, you want to think about this as smart guessing. So educated guessing, smart guessing with confidence bars. So let's say, you try A in the lab and then you try B as an experiment in the lab. Gaussian process will help you decide whether to try C or D next. This is the way it works. So it's a probabilistic model for function estimation. It's used in optimization techniques to model unknown relationships. Basically what you do is you say, I'm going to predict and with what uncertainty will it happen or not happen. So it's using observed data points to estimate new ones, right? So what have you done in the past? And then using that, can you estimate a new data point, and with what kind of uncertainty can you do that? So why is it useful? It enables an efficient trade-off between exploration and exploitation. Exploration is where you're not really sure about that space or that part of the space, and so you want to explore it. It might work, might not. Or you want to exploit. Exploit is where you have some evidence from before that you will probably find what you're looking for. So you can expect a win. And this works really well with limited data, which is very common in lab experiments. And you don't have a lot of experiments, a lot of historical information, and so on. So in our framework, Gaussian process can model the outcome, the outcomes that we care about, like droplet size, creaming rate, and shelf life. And then you can provide physically valid results. So, and you can use PBM for physically valid results, feed that into a Gaussian process to learn the space, and then an optimization technique can search it intelligently. Right, so again, going back to the original point, it's smart guessing with confidence bars, and you can feed into it ideas that are physically valid based on physics-based modeling, and then use an optimization search to find what you're looking for. And then you can vary between exploration and exploitation based on the specific needs. Okay, so we're going to do a demo of what physics-based modeling might look like and how it can feed into machine learning training system. So I'm going to show an app that's going to take as inputs things like the oil type, emulsifier type, oil percentage, storage temperature, and we'll look at two modes. There's going to be a mode 1 which will simulate a formulation. So you're going to select some parameters, and then for a given oil type, the app will use PBM to predict what the droplet size, creaming rate, and shelf life might be using different conditions for processing. And then we'll also have a second, you can enter a full recipe of an existing product, and then you will choose what the potential emulsification parameters would look like. All right, let's get to the demo now. Just kind of getting back to the original point, the models we're using: energy dissipation, Stokes law, Arrhenius equation, and then mixer and emulsifier effectiveness that's encoded into the application. And just a quick heads up, what you're going to see is an output table. It would only return multiple valid results. So only valid results are returned, which are physically stable. Obviously, if you were to build this application as a real product, you could export it, color coding, and you would have a lot of information that will help you understand what's going on in the app. Now, we want to make sure that the app is designed for clarity. So a lab technician, a data scientist, or a product manager can use this confidently and really use it to drive their exploration or exploitation of the system. Okay, one more thing I want to mention, that in addition to what the app will do is it can also generate features, and this is how we integrate that into a ML training system. So we can create features such as droplet size, creaming rate, the oil emulsifier ratio, mixer score, whether it's stable or not, and all of these can be fed into a training system that can then build a model that can predict these values for future input. So how does it work? Once the PBM gives us feasible formulations, ML enters to learn how recipe composition, mixing conditions, and ingredient interactions impact key outcomes. The model picks up subtle non-linearities and generalizes beyond what we manually tested. It becomes sort of a digital formulation intuition, and it's always improving. And that's how these three systems can work together. Okay, and then how do we integrate with optimization? Your PBM can constrain the design space, you don't waste optimization iterations on physically invalid points, right? So if it's not going to work in the real world, let's not even bother learning about it, because physics tells us what works and what doesn't work in the real world. So we use that as a starting point. PBM features can become inputs to machine learning modeling, and then optimization searches can be very highly effective because they never go into areas that are known to not work in the real world. And we don't spend the time and effort and the money required to measure that. Okay, and then the main thing here is that how do we integrate this into an optimization system? You can generate a set of constraints based on the inputs, and these constraints can be used to constrain the search, and that's how you can feed a PBM output into an optimization search. Okay, one more thing before we get to the demo is what this architecture looks like of the application. That you'll see there's a user input, there's a PBM engine that uses that input and generates two things. It can generate features. Features can be used to train a machine learning model. Obviously, this doesn't have to happen every time the user uses the system. You can have the model pre-trained, but then you can also use it only for prediction during the optimization search. And the optimization constraints can be used multiple times. And optimization constraints can be used to constrain the optimization search. Once the search has executed, then you have a set of optimized stable formulations that can be tested in the lab the output can be fed back into the system, and then you can continue testing till you hit your business objectives. So key things: user inputs defines goals or constraints, PBM layer ensures physical realism, ML layer learns the outcome space, the optimization layer chooses the next best settings, and the feedback loop update the model with each round of testing. The hybrid engine turns your formulation process into an intelligent, iterative system. All right, let's go to the demo. I have it loaded right here. So it's an emulsification assistant, multi-mode physics-based modeling plus machine learning plus optimization. Obviously this is a demo, but the physics and the implementation behind it is real. Here I can provide a specific type of oil that I might want to work with. So let's say I do sunflower oil. I can choose to override the percentage in my mixture, right? So in this mode, in the first mode, we're only looking at the oil. In the second mode, I'll show how this can be used as a recipe. So here, I'm saying it's my system's going to have, my recipe is going to have 15% oil. I can change that. I can change the storage temperature, to some degree that I expect it to be stored at. And I can also provide shelf life, and that's an optional thing. So in the first mode, we have the oil and emulsifier. So I'm going to run this PBM search. And what I get is the system for sunflower oil at 15% and a storage temperature of 25 degrees Celsius. It found 9 values. So sunflower oil, 15%. Emulsifier type is polysorbate 80. Obviously, it didn't find anything else. It would have shown that. It found the emulsifier percentage. So how much emulsifier you want to put in that mix, the mixer type that you want to use, the rate, the RPM for the mixer, the storage temperature, and then what we predict the droplet size to be. You want to be under a certain limit. So these settings are under that limit. The creaming rate, again, how much creaming do you expect per day? You want to be under a certain limit, and these are the settings that we're achieving that. What's the predicted, the energy dissipation, and so now we're getting the areas of machine learning features the system generates: energy dissipation, oil emulsifier ratio, shear category, mixer score, and so on. So these are all features that could be fed into an ML system. Now what we do with this is, not only do you understand what the settings you want, so your processing conditions can be set to those, to fine-tune those settings in the lab, but also you can generate constraints that can be used to inform your search. So what we're saying is that there are possible 9 settings, and they all are 10, they're all between the RPM range of 14,500 to 15,000. Oil obviously we set at 15. Emulsifier range has to be between 4 and 5 for sunflower oil. Shelf life would be between 4. You want to use an ultrasonic mixer, and so on. You can obviously download this and feed it into an optimization system. Now let's go to the second mode. So here we have a full recipe table, right? So the idea is you would enter a recipe. So I have a recipe of olive oil, water, sucrose, emulsifier, lecithin, and you have a specific percentage. Obviously I can add other ingredients, or I can change the percentage if I want. I can adjust the storage temperature, and then also the shelf life, the same thing we had here. Now if I run this, great. So for this recipe, olive oil based, I find, or the system finds, the PBM modeling finds 67 valid settings at 12% olive oil. If I were to change this to, let's say 14, and run this search again, this time I got 53 at, and it's constraining it to be what's realistic, because it adjusted the recipe. Since I went up olive oil, it adjusted it in on the water in other places. So it normalized it to 100%, and then it came up with these settings with different types of emulsifiers, different types of mixers, and the specific RPM, storage temperature, what the predicted droplet size would be, what the creaming rate would be, what the shelf life is predicted to be, and then the ML features for energy dissipation, oil emulsifier ratio, shear category, stable, and mixer score, and whether it was stable or not. And again, you can convert this into constraints that can be fed into an optimization search system. So now going back to the slides. So what's the real world usage? The real world, it's simple. A lab scientist enters a combination of a new oil and emulsifier. What's the specific percentages? They receive valid emulsification settings, mixer, RPM, and so on. They extract those as constraints. They feed that into an optimizer, and then new recipes that are suggested are guaranteed to be physically stable because we're using physics-based. Common failures, when this might not work, oil percentage too low, emulsifier is too low, you don't have enough mixing speed or type, mismatch between the emulsifier and the oil, or the storage temperature is too high. But these are all real things that formulators already know. Being ensuring that the constraints are capturing the right combinations, the right levels, and the right settings is critical to constrain the optimization search, so that you only go and explore areas that we know are possible but are not absolutely known to not work. Right? So you can use this for R&D emulsion design, shelf life optimization, formulation to manufacturing handoffs, to constraining the optimization system. A lot of use cases for PBM. Now let's spend some time talking about physics-informed machine learning. So machine learning models trained with physical knowledge built in that's the difference between traditional ML and then physics-informed. So they don't just learn from the data, but they honor real-world laws. And the way it connects to PBM, you have PBM outputs like droplet size. They become inputs or constraints for machine learning models. And the machine learning models can be trained on the lab and PBM data, so they can learn the complex interactions beyond physics. And then physical laws can guide the learning process. So you're not again learning things that we know or physics tells us will not work in the real world. And so why does it matter? It matters because combining PBM plus ML leads to smarter, faster, and more trustworthy predictions for formulators. So if you're building something for a formulator, trust is key. And if you can produce stuff that they look at it and they don't say that, oh, this is not going to work in the real world, then you build that trust and they're more likely to use your system. And that's key to building usage, and then also learning from their behavior and improving the system over time. Okay, so quick summary of what's the relationship between PBM and physics-informed machine learning. PBM is first principles equations. A bunch of these exist. We talked about those. Physics-informed machine learning incorporates the physical laws into ML models as constraints, priors, or loss functions. PBM, what's the role in the workflow? It provides physically accurate predictions for known systems. Physics-informed ML learns these complex patterns while being grounded in physical plausibility. PBM generates outputs and derived features and feeds that into ML. Physics-informed machine learning can be trained on experimental and PBM data, and it ensures that physical relationships are honored. So how do you decide when to use what? PBM is a good fit for when mechanisms are well understood and equations are available. So there are certain things that you have equations for. Emulsification is one such category. But if you don't have physics equations and or the data is noisy, incomplete, but you still want physical behavior, then you want to combine these two things together. But if the equations are not well understood, then you obviously need to learn about that, and then you need to create the data and learn from it. That's where the machine learning part comes in. So we talked about the examples. You can physics will tell you the droplet size and creaming rate that can be calculated using known models. But if you're trying to use that to predict stability or shelf life, then you can use the PBM output as derived features, right? And then feed that into a training system to do those predictions for that specific recipe for the specific conditions. Key integration benefits, trustworthy machine learning. So PIML avoids the black box. By enforcing physics, you can make sure that you produce stuff that is trustworthy, that is believable, and is known to work in the real world. And this is key when working with formulators. Data efficiency, right? PML needs fewer real world data points because it leverages PBM. So you don't have to learn the physics that already is known. The PBM model provides that. And there's more realism when you're doing optimization. Optimization can use physics-informed machine learning to prioritize candidates that are both performant and physically valid. And that's the key point, that you want it to be promising, but also not be known to not work in the real world. Otherwise, you're wasting time and effort. So I think we're coming towards the end, but basically, we want to talk about why PBM and PIML still matter, even if you're doing optimization. And the key point here is optimization alone cannot guarantee physical feasibility or safety. So physics-based modeling ensures constraints are respected and domain knowledge is embedded in the system. So optimization plus Gaussian processes is very powerful because it's agnostic to physics. Without PBM, you might create recipes or formulas that suggest droplet sizes to be below the actual limit that you want it to be, or the emulsifier percentages that lead to toxicity. Physics-based modeling can help you avoid that. So the model explores invalid regions and ends up wasting compute and lab trials if you don't have PBM involved in it. Now, if you have PBM, you enforce your physics-based constraints, and then you anchor your predictions into the mechanistic understanding and not just the data interpolation. Second key point is that physics-informed machine learning generalizes better with less data. So in formulation, data is sparse, costly, and noisy. Physics-informed machine learning incorporates physics-based modeling outputs as features or priors and reduces the amount of training data that's needed. It leads to better generalization, especially for edge cases or extrapolating to new ingredient combinations. And that's key when you have supply chain variability and new ingredients that are showing up that can reduce cost or improve your product while maintaining the current outcomes that you're looking for. PBM enables faster iteration with fewer wet lab trials. Optimization alone needs several initial samples to start learning. Physics-based modeling can generate thousands of virtual experiments in seconds. Optimization can start with this PBM generated data set and refine intelligently from there. PBM also enables a hybrid system that learns from failures. PBM can label and reject unstable formulations before they're passed to optimization. This feedback improves machine learning accuracy and the optimization-based decision making. So you end up with a closed loop system that learns faster and fails less. And last point, real world safety, compliance, and regulatory demands and requires physical models, right? So this is a very key point. Many CPG and pharma applications require explainability, and PBM gives you white box insight into why a recommendation is valid. And that's key when you are in these highly compliance-focused, regulatory determined areas like CPG and pharma. Regulators and R&D managers need this. They're very uncomfortable with black box only, which optimization offers. Having white box insight is key, and optimization can't offer that by itself. But using optimization without using optimization without PBM is like asking, it's like a GPS for directions on a blank map. So it will still try and figure out and explore a way to drive into a lake. You might hit something. What PBM does is it adds the roads, the guardrails, and the speed limits, so that when you start exploring and finding your way, you are less likely to get into trouble. If you only use optimization, you'll waste time exploring bad recipes or need more data. With physics-based modeling, it gives you a map. It gives you a smart co-pilot that learns faster, respects the laws of nature, and this hybrid setup is faster, safer, and smarter for real-world R&D. All right, so in summary, this system transforms formulation work from guesswork into science-backed, data-rich decisions, and it ensures that only valid physical outputs are returned and enables optimization workflows directly. So just to conclude, I think the message is pretty clear. The future of formulation is hybrid intelligence. You use machine learning to learn faster, and you use optimization to experiment strategically. You use platforms like this to make it practical, reliable, and scalable. So let's stop guessing, let's start formulating with intelligence. Thank you.